in the news this year, but it was a couple of years ago. Some high school kids made took a GoPro type camera or other camera and lofted it into the atmosphere. I guess I don't know. Let's see. Is that finished already? Let's run it again. Where's the repeat? Still got 1 minute to go, so let's go. So they lofted it up in a balloon, and I presume attached an address to it. So the balloon goes up, it pops when it gets to some altitude, and then the camera drifts back down, I suppose, on a parachute. Oh yeah, so this is it starting. Yeah, again. So I guess it's self-explanatory. When I looked at it the other day, it started off halfway through, so I guess this catches the early parts of it. Very clever. Just a couple of young kids doing this, and kind of an innovative way to do things. It relates to what we're talking about right now, because we're talking about pressures in the atmosphere, and pressures below sea, etc. And so the mechanism by which a balloon will rise is buoyancy, which we haven't talked about. It's basically due to the pressure differential. So the reason the balloon will ultimately pop is because the air gets so thin in the final moments of this video, where you can see the curvature of the Earth, that the balloon's too big for itself. So you might have seen these weather balloons that are in these kind of loose sack that's filled with helium. It deploys some weather instruments and just goes up into the atmosphere, and as the air gets thinner, as the pressure gets less, and the air around it gets less dense as we go further up, it expands to be larger and larger and larger. So what starts as a small kind of raggedy ball, which is very long, ends up being a big full-blown balloon. Not a hot air balloon, but one that has a different fluid in it. It has something that's lighter than air, which is typically hydrogen. It was hydrogen in the days of the Hindenburg. But as you know, hydrogen is a bit more flammable than other inert gases, and so helium is almost as light, but much less explosive. And so helium is typically used. And so this relates to everything so that's just to start things off on the note, at least in terms of what we're attempting to do in this class. In terms of class prosecution, is there anything we need to take care of? Everything running smoothly? So we're coming to the end of the second week. First assignment was due last night at midnight nominally. It's actually open a little later than that, so that people don't say, well, I was on at 11:59 and 40 seconds and it cut out on me. So it does stay open a bit longer, but it certainly doesn't stay open till now. It's certainly closed. Today you'll have most of the material you need to do the second assignment, so that will be live today. What you won't have will be the stuff on accelerating fluids, which we'll do on Monday, but it's still due on Thursday. So you can count on each Thursday being this deadline. So mark that in your calendars if you would, just so that you don't get caught out. Okay. Anything else we should deal with? I guess I was going to ask whether anyone's watching it online, but of course we can't tell. I guess there's no. Yeah. Okay. Well. Yeah. I guess I've lost the. There's usually a little panel that gives people's identities, I guess, on this. So maybe it's still on here if I look on this. No, I guess not. So I don't know. So I think the other ones that are broadcast may not have had the sound. So what's been done in the past is that if you have a friend who's actually in class and you're not in class, then you text them and you shout at me to turn the audio on, or the fact that the video isn't working. So anyway, do people look at the stuff online? I haven't really looked at the number of hits so far, but I guess you don't need to. I'm asking the wrong crowd maybe to that question. So but anyway, so it's there as a facility to you. The stuff that we're going to do online next week, I think I am going to be here for, and so I'll just continue in class as we've been doing. If you want to turn up, great. If you want to do it remotely, that's fine. That's always your option, I think, in this. I presume that you that you know of our resource page. I might just explain what's there. Every at the end of every lecture, I put some material. So we'll be this one. Right now, there's no content posted, but it will be replaced. There is last year's material on there if you are so interested to look. It may be different or similar to what we
So this is the material we're talking about.
And so you have a variety of resources. So this is a short week, of course, as you know. So 2.1 and 2.2 is today. 2.3 we won't do, but 2.3 is actually put on there as some examples. Oh, wrong one, sorry. So if you look at, you might look at 2.3, there's some examples, work through in the same way. They follow directly on from these notes, and so you're welcome to look at those.
Before we go through examples,
just as an extra resource. So it is kind of self-paced. It can be self-paced. There's no reason why we can't also make the assignments live earlier, and people so wish to have access to them. But for now, I think we'll just do it incrementally as we move along. All right, so you have those resources available to you. Okay, everyone's very quiet this morning. So, all right. So where is the material that I want? I guess it's this. Don't know why it's so small, or large rather. All right, so the material today that we'll go through is the material, we went through that, is for 2. Yes, I'm back. Did I miss it? Sit here. All right. So let me get this going. So just don't know why this is so large. All right. So this is our plan for today. To recap exactly what we talked about last time, and then take it the next step. So the summary from last time, as you remember, we went through some derivations. The basic outcomes, I think, were that pressures at a point are the same in all directions, and so we can define them just by a magnitude P, a scalar value. If we look at fluids which are static but are accelerated, we end up with a number of relationships by resolving in the different orthogonal directions, z vertically upwards, x and y horizontally in the horizontal plane. And as a result of that, we get a number of simple relationships which we can write in this form, or in this form here. Perhaps divide this out. So perhaps the most interesting one that we deal with is the one for behavior in the vertical direction, which if we write it out in longhand, don't know why it wants to keep that strange identifier here, is just the change in pressure, unit weight, is equal to density times the acceleration in the z direction. And so this is the expression that we had last time. When we looked at cases where there's no acceleration, this goes to 0, and we're only left with this term here, which is exactly this, either as a partial derivative or as a ordinary derivative. Doesn't matter which one we relate it as. We've integrated this before, and so we know that as we go down in an incompressible fluid, the pressure changes linearly as a function of unit weight, because unit weight is constant. This expression, we said, is always true. It's true at an individual location. Even if the density is changing in space, it's true at every particular point. And importantly, we also know that when the accelerations are 0 as well, then the pressures in the horizontal plane are 0. Pressure changes. So you go from one point to another in the same fluid, which is displaced from it by some amount laterally, and the pressure doesn't change. And so that's what you might expect from a swimming pool. And I guess the corollary of that is that if you look at the surface of water, then that also has to be horizontal as well, because that has 0 pressure on it, atmospheric pressure acting on it. And so that has to follow the same rules. And so I guess this is kind of a consequence that liquids always come to some equilibrium horizontal arrangement. So if you're trying to put a foundation in for a house, one way to take level from one location to another is to get a big long piece of Tygon tube, which is clear, or a garden hose, fill it with water, and you know that the water level in the tube at this location on the foundation and is exactly at the same elevation as the water level on this side. So you can actually transfer a level across a foundation. We also noted that if the unit weight changes as a function of pressure, then we can't use this expression, and we have to resort to something else. And so what we do is we resort to replacing the unit weight, which is equal to gravity times density, by replacing this by the ideal gas law, which I guess we can rewrite as density is equal to pressure. I'll try and make my vertical lines over RT. This is the gas constant for that particular fluid, whatever the fluid is that we're talking about. This is temperature, and we can integrate it to be able to get a change in pressure with elevation, and that's what we ended up with last time. And so that's what we'll begin with today also. So, what are the consequences of this? One everyday consequence of what we have here with these two relationships, dealing with the one at least for the incompressible fluids, is, for instance, we're talking about these presentations that you might give on of some curious topic, and we'll set the groups for that for next week, for next Wednesday, and then you can meet with your groups. But one topic, a simple question to ask is, for instance, we typically have storms. 2 years ago, during this class, Hurricane Sandy rolled in over New York and New Jersey, over the eastern seaboard, and wreaked havoc on the shoreline because there was a high tide combined with the storm surge due to the hurricane. And so one question that at least we're able to answer now that you might ask is, if you're looking at a hurricane or a tropical storm, what is the reason for the storm surge? And so I think for Sandy, the storm surge was something of the order of 6 meters. And so the question is that due to just the low pressures which are present within the center of the storm? Or is it due to, for instance, the fact that in a cyclonic twist you get some water bulldozed up onto the shoreline and some bulldozed away from the shoreline, and so there's a differential tide caused by the winds? And so we're in a position to at least be able to answer whether the storm surge is purely due to the low pressure. So this is just a wiki page on the Labor Day hurricane, I guess quite topical in 1935, quite topical for us since it was Labor Day, and Labor Day's just passed. But the pressures in the center of the storm, looking at the lowest pressures ever, are of the order of something like, what is that, 100 instead of, so this is almost, 1 bar would be 1,000 pascals. And so this is less than that by about 120. So 120 pascals. And so the reason that you get portion of a storm surge, I guess this is turning out to be longer than I thought, is that if you think about the surface of the sea, which is usually horizontal, if, for instance, you had a pressure in the center of this which was lower, then you'd expect that this lower pressure here, PC, would physically suck up the water. And the reason for that is that on the outside, where the pressure is atmospheric, and we know the atmospheric pressure is about 100 kilopascals, kPa. And from what we know about this, as pressures in the horizontal plane in any fluid being constant, we know that the pressure here has also to be the atmospheric pressure, 100 kPa. And so if there's water above that, then this water has added to the pressure of this point. So for instance, we could subtract off the pressure that we go up to this point, and this has to be something like 90 kPa. And so the difference between those has to be equal to, so in other words, we could write that as the difference between PC and PA is about 10 kilopascals, and that has to be equal to the unit weight times the height of that bulk. And so the unit weight of water is about 10 kilonewtons per meter cubed, so that corresponds to about a meter. And so if you think that the storm surge is purely due to that low pressure, it certainly contributes to it by adding 1 meter, but to get 6 meters of storm surge, then if you want this actually to be 6 meters rather than 1 meter, then you have to take the coast of New York or wherever it is, and have this being bulldozed onshore, this being bulldozed offshore. And you can imagine that if you have some air pulling across the top of the ocean, it provides basically a shear stress to it. And this shear stress, just like in viscosity, in the problems that you've done in your assignment, will add to, basically bulldoze the water up against the shore. So we're able to at least make some calculations with what we've done so far. So what we'll do today is we'll try and use what we've understood so far to be able to calculate how pressures vary within fluids. And specifically, we'll look at manometry. And we'll come out of this with a number of rules, which are written in shorthand here. And basically, there are 5 or so rules. The rules are, if you go up in a fluid, then the pressures decrease. If you go down in a fluid, the pressures increase. If you go horizontally in a fluid, the pressures don't change. If the fluid is evacuated and in contact with a liquid, it's always at its vapor pressure. And if we go up and down in a system where the fluid is a gas mixed with liquids, then we typically don't care about the unit weight of the gas because it's, as we saw, the density of air is about a kilogram per cubic meter. Density of a liquid, water, is of the order of 1,000 kilograms per liter. So there's a factor of 1,000 difference between them. And so we don't care too much about that. So that's our plan for today, is to look at manometry. We went through a bunch of this last time. You'll remember when we talked about compressible fluids, what we did was we wrote the rate of change of pressure with elevation as a function of the ideal gas law, and we integrated that to come up with an expression, which was maybe the last expression we had last time, which was this expression here. And so we were able, for instance, to be able to figure out, and you can go through this again, it was the last activity last time, we can say something about how the pressure at some other location varies as a function of maybe a place that we know. So the place we might know would be the pressure at sea level, where we know it's 100 kilopascals air pressure. And this might be some other location that we'd like to be able to calculate the air pressure. And so to do that, we just integrated this between those 2 points, and by convenience, we exponentiated both sides to be able to get rid of this log. And so we had a straight magnitude of pressure. We could have left it in the other way. An implicit assumption in that, though, if you remember, was when we wrote this, is that we didn't write this with the temperature inside the integral. So implicitly, we assumed that the density was changing only as a function of pressure, and therefore an implicit assumption in that was that as you go up in the atmosphere, the temperature remains the same. So at sea level, it's 20 degrees centigrade. At 10,000 meters on top of Everest, it's also 20 degrees centigrade, which typically is not the case. We know that just heuristically. And so what we could also do, and what we will do just briefly today to get things started off, is we could also do this integration where we include the magnitude of the temperature, but not keep it constant, but have the temperature change as a function of the elevation. And so I won't bore you with the calculation for that, but this is the outline of it. And so the idea is that if we include the temperature in this integral, then we merely have to be able to define exactly how temperature changes as a function of elevation. And this is just a graph. It comes out of your textbook of the change in elevation as we go up from sea level, which is here, 15 degrees, I guess, in this particular case, to the top of, well, 10 kilometers would be 35,000 feet, a little bit higher than Everest, and beyond up to the edge of the atmosphere, where it first decreases, gets colder, stays the same, and then gets warmer, slightly warmer as we go up into the atmosphere. And so what we want to do is we want to be able to define the temperature as some function of See? And it's not very easy to do that in the case where we have this whole curve, but certainly we can do it for the first part of this curve, right? And so if we start off with this point here as being our reference point, which is temperature I think we probably want that, right? We want this as T0. And so T0 in our particular case is something of the order of plus 15 degrees centigrade. We want to go up 10,000 meters, and we want the temperature to be something like minus 60. So I guess 60 to 0 is 60, plus 15 is 75. And so we want this value to be something like 75 degrees centigrade over 10,000 meters. So 10,000 meters is 10 to the 3. 10 to the 4, right? Sorry. And so we can check our dimensions, right? Temperature has to be equal to temperature. Temperature has to be equal to temperature divided by height multiplied by height. So this is going to be temperature also. And so this is just going to be equal to, what is it, 0.0075, is that right? So 75, 1, 2, 3, 4. So this would be in degrees centigrade per meter. And so if we substitute this value in for this component here, substitute that in for here, I won't bore you with the integration. It actually comes out a bit easier than it did before, but the ending relationship is just this. So it's a function of how the temperature changes with elevation. If it changes faster, it would be a larger number than this. The actual elevation, the reference temperature at 15 degrees at the base of the atmosphere, and we can use that to be able to calculate what's going on. Okay, if we do that, we can do it very quickly. This is just a little piece of code to do that. Let's do this. See if it will. I think it will. And you see that if you look at the temperature, the pressure change with elevation. So this is elevation on the bottom, 0 elevation, 10,000 meters. I think the top line is where we assume that the temperature remains constant. The bottom line is where the temperature is changing with temperature according to what's behind. And it goes from 100,000 pascals, 100 kPa at ground surface, to, if you're on the top of Everest, to be something like 40% of that. And so the difference between these, actually it gets to be a larger fraction of the absolute pressure change, right? This is the absolute pressure. We have to use absolute pressure to be able to evaluate this. So this is absolute pressure. Atmospheric pressure, which we call 0 here, is 1,000 kPa absolute. And as we go up higher, we find that the air gets thinner, less dense, and as a result of that, the pressure reduces. And so the other way to look at this, which I think is useful, I think I copied this before. Actually, I think it's open. One of these windows is open. I'm trying to look for the... So is it this? Let's see if this is arranged. Oh yeah, this is it. So this is exactly that graph. We've turned it around to put it in a way which is something a bit more similar to what we've looked at ourselves. And so this is what? This is elevation. This is Z. This is pressure. And this is, if you like, atmospheric pressure. So if we wrote this as atmospheric pressure, this would be 0, and this would be minus 100 kPa in terms of gauge pressure. And so you see as you get farther and further up, it's becoming more and more vertical, which means it's changing less and less. And it will ultimately asymptote to it should actually asymptote to what we think of as 0 pressure, right? Which is this value here. This would be minus 100 kPa, which is actually 0 gauge pressure. if you look at what would happen in the ocean, what would this figure look like as we transit that? We've drawn this figure before in as a pressure versus an elevation. As we go up, it asymptotes to some number. If this is sea level here, we said that at sea level, now the pressure change becomes constant. And so the reason for that is that this change in pressure with elevation dz is equal to dp. Since we've also got this equation that says that the change in pressure with elevation is equal to minus unit weight over 1, then we could also write this as 1 and unit weight, right? And those triangles should be the same shape. They have the same units, and therefore they're the same shape. So we could calculate what the gradient of this curve should be at this particular point, and what would it be? I guess it would be equal to the unit weight. So this is equal to, if we would draw where this goes into the water, the gradient of this curve would be, the height would be 1 meter. This length here would be 10 kPa. So this is 10 kilonewtons per meter squared, meter cubed. And so it means that as you go down 1 meter, the pressure changes by 10 kilopascals. And so in other words, 10 kilopascals would be 10 to the 4. And so in other words, if you drew this, this curve to the same scale as this, it would look something like this. It would be very flat. It would almost be horizontal. And that's because the unit weights are a factor of 1,000 different from each other. Unit weight of air versus the unit weight of water. And so it's always useful for us to think about this as being how the pressure changes in air as we go down here, because this is curved. In water, it would be straight, but in fact, in water, it would actually look more like this. It would actually be 1,000th of the grade. It would be 1,000 times flatter than this gradient here, just by the relationship we understand. Okay, so that's useful to at least understand, hopefully. Okay, so we know something about pressures in fluids. We've already recapped this, if you like. So our exposition, are we okay? Our exposition of this is that pressures at a point are the same in all directions. Pressures are constant if we go horizontally. We've used that already. And as we go vertically, pressures change by an amount equal to the unit weight. If we're in a liquid, we can get that very simply by using this expression. If we're in a gas, then we can't use that expression. But from what we just said about this behavior that we drew on this graph, maybe if we're in a gas and we're moving up, we don't have to care, because the change in pressure is so slight. In other words, the width of this graph in terms of pressure is so small compared to how it is down in the liquid part, we can ignore the fact that the unit weight of the gas is anything at all. So that's the rationale for that. And so what we can use this for is we can use it for manometry. So manometry is where we use heights of liquids to be able to measure pressures in systems. And the most classic case of that is to use a barometer, a mercury barometer. Of course, mercury is not, it's an outlawed substance these days, but let's listen to this anyhow.
We're going to make a barometer. And what I have here is a glass tube that's about 800 millimeters long. And I've filled it with mercury almost to the top. And I'm going to finish filling it so that I get filled all the way to the very top. And then I'm going to put my finger over the end, and I'm going to invert it into the mercury. I'm going to set it here and use our
wonderful stuff, mercury
clamp to hold it. Now, what's keeping this mercury
Whoops, I didn't do that.
column so high? It's that atmospheric pressure pushing down on the mercury, pushing this up. And let's see how tall our column is. 744 millimeters. It doesn't matter what size the diameter of our tube is, as long as it's relatively small.
That's enough, Missy. All right, so Mercury Barometer. I think it's kind of a grade school example, but useful anyway. It illustrates the point. We now know physically how that works and are able to explain it. It's actually very similar to the example we just did with the storm surge rise as a function of any hurricane. And we used one extra piece of information. The one extra piece of information that we've said already is that a liquid in touch with in an evacuated component has to exist at its vapor pressure. There's no other outlet to this system. So what we can use from before is to know that outside the mercury on the outside, the pressure at B has to be atmospheric. We don't know what that is. The average atmospheric pressure is 100 kPa of that order, 103. But we want to measure that more accurately. We know that we can go from this point through the same fluid to a point at the same elevation. So height hasn't changed, so the pressure at B prime has to be the same. And then we can go up through the fluid, and we know that the pressure should decrease as we go up this amount. And we know that decrease because we know what the height is that we go through. And so what we can do is we can just do it by calculating the pressure here, adding this weight of fluid here. So the vapor pressure exists at the top. We go down by adding a weight of fluid, which is its height times its unit weight, and that has to equal the pressure at B prime, which has to equal the pressure at B, which is equal to P sub B. And so if we know what the vapor pressure of mercury is, which is a very, very small number, here in English units, but also a very small number in SI units as well, negligible compared to all the other units. If we measure the height, we know the unit weight of mercury, which is something like 13 times the unit weight of water. Then we can calculate the atmospheric pressure. And so we just set this equal to 0, and we have this relationship here, which allows us to calculate barometric pressure. And it's something that's been used to define behavior. And it turns out to be something like 30 inches of mercury, or 744 millimeters. That doesn't sound right. That is about right, right? Yeah, almost a meter. So if you did it with water, you could do exactly the same with water. Put water in a tube, turn it upside down. But the reason you use mercury is that the tube you'd have to use for water is something like 35 feet. Yeah. And so it means that you couldn't do it in one room. You'd have to have 2 or 3 stories. Typically a story is 10 feet in a house. And so you'd have to go up that. And so the water is cavitated. So it's exactly the same reason that if you want to suck oil out of a well or water out of a well, you don't suck, you actually push, right? You can only lift it maybe 34 feet before water cavitates, and you'll just get vapor out of the well. So the same physical reason for that. And so that's the mechanism that we'll use for measuring lots of different pressures using similar instruments. And we'll always use the same technique. So let's go through a couple of other examples. So one example that's no different from the mercury case, but doesn't have vapor pressure involved, is what's often referred to as a piezometer, or you can think of it as a well. Exactly the same thing. If you want to calculate the pressure at the bottom of the Macondo well with a static fluid in it, or within the Macondo reservoir for that matter, where you're not going through the well, it's actually a very similar calculation, is you just realize that at the top we have atmospheric pressure, and typically we'll take atmospheric pressure in this as equal to 0 gauge pressure. And as we go down from this, the pressure will increase equal to, so just the pressure change here, delta P, is just going to be equal to the unit weight of whatever the fluid is multiplied by H1. So nothing else. And you can, so where the fluid is a liquid, density is constant with depth, then we can easily calculate what the magnitude is in the system. If you fill this region here and actually the standpipe up with sand, but so that there was still a connected path through that sand all the way down into the reservoir where the rocks are also sand maybe, then it'd be exactly the same calculation you've made. All that matters is that the fluid has to be connected, there has to be a pathway all the way through it. If there's a blockage, such as if you sheared off this well, for instance, or you put a plate across this well, then you can't do it. But as long as it's simply connected, you can always make that calculation. And so, with a couple of caveats there. So those are the simplest, that's the simplest kind of manometer. Standpipe piezometer is the simplest manometer. It gets a bit more complicated if we start with systems which are a little bit different from that. And so manometers are cases where, for instance, you might want to measure pressures which are subhydrostatic. And they typically involve a vessel. And so this is a vessel, or you could think of this as a pipeline coming out of the page at you, which is tapped by a tube. And the tube has a gauge fluid in it. And so typically the way to be able to do this calculation is to be able to work from one location to another. And so the calculation is here, but we can just do it in this class. Typically, we'd like to be able to figure out exactly what the unknown pressure is. So the unknown pressure here would be this, which we don't know. The known pressure would be the pressure here, which I guess would be atmospheric. And so the easiest way to do this is to use those manometer rules that we talked about before and just write a simple equation. So the equation we're going to write is that the pressure, the atmospheric pressure at point A, which is this point, we go down to this point here. We know that because we know that once we're here, we can go through the same gauge fluid and get to this point here, which has the same pressure. P3 and P2 have to have the same pressure, right? By what we've said about a horizontal line. And so as we go from here, we have to increase the pressure by a magnitude of H2 times the unit weight of this fluid. So we add the height H2 times the unit weight of fluid 2. So that gets us to this point. And now to get to this point here, which is the same as this point here, we add an amount equal to minus H1 multiplied by the unit weight of fluid 1. And that has to be equal to the pressure at uppercase point A. So what we're doing is we're working through the system, and we're using those rules that we talked about previously. I'll just flip back to remind you of them. They're on the kind of summary sheet. We're using these rules, these manometer rules, to be able to do that. If we go up in a fluid, we subtract. If we go down in a fluid, we add. If it's evacuated, it's at the vapor pressure. If it's a gas, we haven't done anything with the gas yet. If it's a gas, we ignore the pressure. And if we go horizontally, we merely transfer the pressure across from one location to the other one, even though we're going up and down a tube and up a tube. So that's just shorthand for the only rules that we have to apply in this. Okay? And so now we know atmospheric, it's 100 kPa. We know this height and unit weight. We know this height and unit weight. And actually it turns out that we can get it exactly the same expression as this here. So in this particular case, I can't remember what the problem definition is. If fluid number 1 is a gas, which it could be, obviously the gauge fluid can't be a gas, it has to be a liquid, then this term we would just put equal to 0 and ignore it. And then the actual equation would be that the relative pressure at PA is equal to this height times the unit weight of the gauge fluid. So in other words, in a simple case where this is a gas, the height of this difference between the two limbs of the manometer is actually the pressure differential between atmospheric and otherwise. Okay? So that is all that we'll end up doing. So the manometer rules are written, but those are the only things that we're ultimately doing. So I'm trying to think as to what we have in each of these. We have a number of different examples. We can go through some more, but they're relatively straightforward to understand. So for me, the easiest way always is to write it, to first of all make one choice. One choice is the place where you'd like to calculate the new pressure, and that is the last term that you'll fill in your equation. And the first one is the one that is furthest linearly away from that. So in this particular case, I've kind of maybe done that backwards. But so if we're solving this, I'd know that I would know this value here. I don't know the value here. And to be able to do this, I would just write the expression starting from this point and ending up at this one. So it would just be P atmospheric. I'd go down to this point here where I know the pressure is going to be equal to adding 5 plus 2 meters multiplied by unit weight of mercury. Gets me here. If this is a gas, then my job is done because I have the number. If it's not a gas, then I have to go up to get to this point here. And so I have to go up this height, and I have to come down this height. And so I could do that just by, if I wanted to, I would go up by subtracting off 2 plus 5 plus 5 multiplied by the unit weight A, which gets me here. And then I go down 10. So it's going to be plus 10 times unit weight A gives me the pressure at A. And of course then I'd realize that I didn't really need to do that. I really only needed to go up to this point here, which is exactly at the same height as this. And of course the difference between these two terms here, they only differ by this magnitude of 2. 5 plus 5, minus 5 and plus 5, minus 10 and plus 10 here just cancel out from each other. And so it's just a matter of being able to figure out exactly where you go with this. So it's relatively straightforward. You'll get used to doing this. So we're using the manometer rules. We just need to know when we go up, we subtract off a pressure. When we go down, we add a pressure. When we go up, we subtract it off a pressure going up here. When we come down, we add a pressure going here. And in this case, we know hopefully the unit weights. We know the heights, all of the heights. We assume a magnitude of atmospheric. Typically, if we're working in gauge pressures, we take atmospheric as being 0 gauge pressure. And so we calculate the pressure at point A in gauge pressure. And so you'll remember the little diagram we had before of 0 pressure. If we plot pressure versus, so this is 100 kPa. This is 0 gauge. Zero gauge pressure. And so in going down from this, this is minus 100 kPa. So this is absolute pressure. This is 100 kPa absolute pressure. And gauge pressure is 0. And this would be minus 100 kPa. So it depends on where you are in this range. So typically we're atmospheric or above, but of course you could be anywhere in here, in which case the atmospheric pressure, absolute pressure would be equal to this height here, ABS, and this would be gauge pressure. Not a very good diagram. I guess if you look here, I think we have a better, there's one drawn out somewhere. This. Exactly that. So it's just make a choice of understanding the difference between gauge pressures and atmospheric pressures. So this is 100 kPa. The pressures we measure above this are gauge pressures, and relative to this, the total amount to 0 pressure is absolute. Of course, the pressure we find ourselves at could be subatmospheric, in which case we have a negative gauge pressure, but absolute pressures always have to be positive by definition. And of course, absolute pressures are the pressures we use in the ideal gas flow. Absolute pressures and absolute temperatures. So don't forget that. All right. So what else do we have here? Manometry. I wanted to get to. There are a couple of other examples. They all revolve around the same ideas. If systems are closed, then I think you always have to get used to figuring out what is the unknown that I'm trying to figure out, and which are the known pressures in the system, and then start writing the equation from the known pressure that you have. And so the examples that are done here are all in terms of that. You can imagine also that if you want to measure pressures quite accurately, what you might do is actually put a manometer on its side. So instead of measuring the difference between the elevations in the manometer from one arm to another, which is measured vertically, which if the pressure differential you have is relatively small between the one limb and the other, or between pipeline A and pipeline B is relatively small, then the height change is going to be small and you can't resolve it very well. One way to measure it more accurately is to lay the manometer down, so that instead of measuring this height difference between here and this point here, which is, in this case, isn't small, but it's certainly smaller than measuring the length of the rise of this along this inclined component. Obviously, as this limb becomes flatter and flatter, it will become more and more resolved. It'll give higher and higher resolution of the pressure differential between the two pipes. And so an inclined tube manometer is something to do exactly that. Of course, the inclination of it can't be more shallow than the fact that this upper limb would come in contact with this other thing and flow into this pipeline, obviously. And so there is a limitation to it. But you can imagine that you could use that. And so you can derive an expression for that. And not surprisingly, the expression is that if you measure the length along the rise of that manometer and its inclination, that gives you a proxy. This is basically the change in height, delta H2, that exists between these 2 points. So the height between here, this would be, if you like, delta H2. Sorry, straightforward. So manometers are what have been used since the time of Isaac Newton. Still very robust. There are other ways of measuring pressures, of course. And they are mechanical and electronic devices, typically electronic devices these days. Mechanical ones would be a typical pressure gauge, sometimes referred to as a Bourdon gauge, And it's basically just a metal tube which you change the pressure in, and because it has a bend in it, as you change the pressure, the tube tries to expand like a balloon, and the expansion of the tube along one side of its outer arc versus the other side of the outer arc is differential. And so you get a larger, as you increase the pressure, I think you get a larger expansion on the outside, and so it bends over. And as it bends over, then you can use this, for instance, in old gauges, to basically turn, usually it runs a little lever down with cogs on it. Those cogs turn cogs on a dial, and that dial is like an analog watch. It shifts over and measures the pressure, exactly that. You could also measure the distance change with something like an LVDT, linear voltage differential transducer. In other words, a rod that runs through a magnet. As the rod is moved through the magnet, it induces a voltage, and that voltage you can calibrate relative to the magnitude of displacement. And so you can calibrate the displacement that you get of this either with an LVDT or with a mechanical gauge to figure out exactly what the pressure change is that it's measuring. Simple as that. But by far and large, the most usual way of measuring it is by using a pressure transducer. And typical pressure transducers are very simply a diaphragm which has a pressure applied against it. As you apply a pressure against the diaphragm, that diaphragm bends, and you measure the deflection of that diaphragm with some instrument. And so typically the instruments you measure it with either are some strain gauge, which is typically something which as you shorten it or lengthen it, its resistivity changes, electrical resistivity changes, and you measure that change in resistivity to give you a calibrated displacement, or you do it with a vibrating wire strain gauge. And vibrating wire strain gauge is just the same as a guitar. As you change the tension of it by moving it, the characteristic frequency it vibrates with changes. So you have something that plucks it electronically, a magnet. You turn a magnet on to pluck it, and you measure the characteristic frequency as it vibrates, and you use that to be able to measure the stretching of the strain gauge, which in turn gives you some information about the buckling of this diaphragm, and you convert that into a calibrated pressure. Or I guess now you use PZT crystals. So PZD crystals are things that when you compress them with a stress or a pressure, they develop a voltage. They're just semiconductor crystals. And so those are then used also to be able to measure magnitudes of pressure changes. And so that's kind of what we'll say about manometry. The assignments to do are mainly about manometry. There'll be some about accelerating fluids. And so everything that we've talked about so far, you'll be able to do about 2/3 of the Thursday's assignments, which we'll make live available for you now. I think there are some questions on accelerations, which we'll talk about next time. And also remember that since it's a short week, we've had 2 classes. There are some examples in class 2:3, which would be our 3rd class of this week, which we won't go through otherwise. They're online. If you want to look at them, your choice. They're available to you to use as you so wish. Okay. Have a great and safe weekend. See you guys on Monday. How you doing?